to Module 3. We are now in the concluding leg on finite difference method, wherein we would consider application of FDM to few scalar transport problems, and we will also discuss few computational aspects. That is to say, you take up the case that if you want to implement finite difference method using a computer programming language, which are the aspects which we ought to consider. So these were two things which we are going to do in this lecture and possibly in the next lecture as well. So our module outline, we have already covered the shaded parts. Today we are going to focus on applications of FDM to scalar transport problems. Before we proceed further, let us have a recapitulation of what we did in the previous lecture. We discussed implementation of boundary conditions, specifically the ones which involve derivative boundary conditions, wherein we need to come up with suitable finite difference approximations of the derivatives. And then we discussed features of the finite difference algebraic system which we obtain from discretization of our continuum problem. So we discussed in detail nodal discrete algebraic equations and what we mean by computational molecule or stencil in the context of finite difference discretization, and we briefly looked at indexing and storage aspects as well. Now in today's lecture we are going to focus on applications of finite difference method to scalar transport problems. We would initially focus on simple 1D heat conduction problems, and later, if time permits, we will take up two-dimensional heat conduction and advection diffusion problems. So outline of the lecture, we would try and apply finite difference method to one-dimensional heat conduction. Now today I would introduce yet another concept that is related to the choice of our grid, which we call cell-centered grid, and the cell-centered grid is specifically of great importance in the context of Navier-Stokes solutions, wherein cell-centered grids are primarily used. The nodes at the cell center, they are used for the discretization of all scalar quantities, and the nodes on the surfaces of control volumes, they are used for velocity components. So keeping that in view, now let us have a look at a cell-centered discretization applied to our one-dimensional heat conduction. We would see if it offers any advantages. Then we will briefly discuss that so far whatever algorithms which we have developed for one-dimensional heat conduction, if we want to implement, we want to write a computer program, so what are things we need to consider, and then if time permits we will move on to application of finite difference method to two-dimensional heat conduction and possibly to advection diffusion problem. If not, we will cover these two topics in the next lecture. Now let us come to our first application, one-dimensional heat conduction. So let us consider steady state heat conduction in a slab width L with thermal conductivity K and uniform volumetric heat generation. So for this problem we have already derived our governing equations earlier in module 2. Just reiterate. Let's rewrite our governing equations. Governing equations and boundary conditions in this case based on Fourier's law are K del to T by del x square plus Qg is equal to 0, wherein this K is thermal conductivity which has been assumed to be constant, and T is the temperature and Qg or volumetric heat generation. Now suppose two ends of the slabs, they are being maintained at two different boundary conditions. Like at the left end, that is x is equal to 0, we have got temperature specified. See, T is at 0 is equal to T bar, where T bar is specified temperature. Next, let us suppose the right end of the wall or slab that is exposed to the environment and there is a heat loss due to convection. So in that case the convective boundary condition becomes minus K dt by dx at x is equal to L. This is our heat flux. This would be equal to H times T minus Ta where T is the temperature at the wall and T is the ambient temperature, H is our convective heat transfer coefficient. So now let us derive the finite difference approximation for this problem. So for derivations, let us move on to a board. So we are dealing with one-dimensional steady state heat conduction. For the sake of reference, let us rewrite our equations on this page as well. So we had our governing equation given by K del 2T over del x square plus Qj is equal to 0. Let us number this as equation 1. Then we had two boundary conditions, T at 0, that was given by T bar, let us call this equation 2, and the third boundary condition was given as minus K del T by del x at x is equal to L H into T minus Ta. So let us call this as our third boundary condition. So the physical problem is something like this our slab. The left end, that's where we fix our coordinate origin. So this is our x direction. So we have got temperature specified here, T is equal to T bar, and we have got convection to a medium which is being maintained at temperature Ta, and convective heat transfer coefficient is given by H. Now for finite difference application, let us discretize our domain, that is the first aspect. So our first task is, or step 1, discretize the domain. Since it is one dimensional problem, we need to consider only discretization along a line. So domain would now be given by 0 to L, and let us choose, for the sake of simplicity of our discussions today, that choose a uniform grid delta x, which is given by, if you use n divisions of our computational domain, the total length is L. So delta x would become L by n, where n is number of divisions or we can also call it number of cells. So now let us draw our one dimensional grid with the proper grid indices. So the leftmost node, we will, at x is equal to 0, we would number it by 1, 2, 3 and so on. Then a generic node I, and around that we will have nodes I minus 1 and I plus 1 and so on, and towards the end we will have the last node. Since we have got n divisions, the last node would be numbered as n plus 1. Our next step would be finite difference discretization, that is, obtain discrete form. So FDM discretization, it will consist of obtaining discrete form for our governing equation and boundary conditions. So now first let us obtain discrete form for it, our governing equation, form of equation 1 at an interior node. By interior node we mean any node other than node 1 and n plus 1, both of which are on the boundary of the domain. Node I, and let us use 3-point central difference scheme. For discretization of our derivative. Discretization of second order derivative. That is to say, this our del 2t over del x square at the interior node I, we are going to approximate it in terms of the nodal values at the grid point I minus 1 and I plus 1. So, central difference formula which we have learnt earlier, this is simply T of I plus 1 plus T of I minus 1 minus 2 Ti divided by delta x square on our uniform grid. So, this is the approximation of the derivative which is involved in our governing equation 1. Let us call this equation as 4. So, if you substitute 4 in our equation 1, so then we get discretized form. Thus, discretized form of equation 1 is k times T of I plus 1 plus T of I minus 1 minus 2 Ti divided by delta x square plus our Qg term evaluated at node I. This should be equal to 0. Let us rearrange this equation. So, we can multiply it by delta x square by k, keep these unknown temperature terms on left hand side and the known source term, let us shift it on the right hand side. So, if you do that, we will get T of I minus 1 plus 2 Ti minus T of I plus 1 is equal to Qg of I delta x square divided by k. So, this equation holds good for all nodes. For all nodes I is equal to 2, 3 up to n. So, this is a discrete form of our governing equation which has been obtained using central difference scheme. Now, let us compare it with the generic equation which we wrote earlier, generic discrete equation. So, compare with generic discrete equation which we had written as AW TW plus AP TP plus AE TE is equal to QP. Now, let us recollect the correspondence between this compass notation and our indices. So, this P stands for our node I, E stands for the index I plus 1, and W stands for index I minus 1. So, if we compare equations 5 and 6, we can easily see that our AP is equal to 2, AE and AW, they are both equal to minus 1, and QP is equal to QG delta x square divided by K, QG evaluated at grid point I. Okay. So, now we have been able to discretize one part, that is our differential equation. The next part is we have to look at the boundary conditions. So, now let us discretize the boundary conditions. So, discrete form for boundary conditions. At node 1, what we have? T, so node 1, that is which corresponds to T is equal to 0, temperature is specified as T bar. So, the equation becomes very simple here, hence discrete equation for node 1 is T1 is equal to T bar. Let us call this equation as 6. So, if you compare it with the generic equation, what we have for this, thus our AP of for node 1, this is equal to 1, AW of and AE for node 1, they are both 0, and QP for node 1, that is T bar. Next, let us move on to the rightmost boundary. Which corresponds to our node n plus 1. So, at node n plus 1, we need an approximation for a derivative dt by dx, and the simplest approximation which we are going to choose is our 2-point backward difference scheme, which will involve values at n plus 1 and node n. So, now let us approximate this dt by dx using BDS. So, we can write this as Tn plus 1 minus Tn divided by delta x. Substitute this approximation which we derived in our convective boundary condition. Thus, discretized BC at node n plus 1 becomes minus k times Tn plus 1 minus Tn divided by delta x is equal to h times, on the right hand side t, that t corresponds to Tn plus 1 minus Ta. Now, let us rearrange the terms a little bit. So, we can write this as Tn plus 1 minus Tn is equal to minus h delta x by k. We have transferred this delta x and k to the right hand side. We have also transferred the negative sign. So, we get minus h delta x by k, which multiplies Tn plus 1 minus Ta. Transfer the unknown variable Tn plus 1 to the left hand side. So, let us rewrite this equation as minus Tn and collect all the coefficients of Tn plus 1 together. So, we get 1 plus h delta x by k Tn plus 1 is equal to h delta x by k times Ta. So, let us call this as equation 8. So, if we compare with generic discrete equation, or generic discrete equation. So, we get AW is equal to minus 1, AE is equal to 0, AP, let us put this AN plus 1 is superscript. So, APN plus 1, this is equal to 1 plus h delta x by k, and our QP n plus 1, that is h delta x by k times Ta. So, now we have got all the equations at all nodes in discrete form. So, our final algebraic equation can be written as, so finite difference algebraic system becomes, now let us write it out in the matrix form. For node 1, what we had, the coefficient of let us put the matrix, let us put the unknown terms here, T1, T2 and so on, as Ti, Ti plus 1 and T of n plus 1. On the right hand side you get, at the first equation, that T1 is equal to T bar, so QP1 that was equal to T bar. For the second equation onwards, we had this term, let me put it as QPI. The expression for QPI we have already derived earlier in the previous page. So, it continues as QPI for all the terms from 2 to n, and for Tn plus 1 we had the last term, let's rewrite h delta x by k times Ta. So, this completes our right hand side. Now, let us come to the left hand side. In the first row, the only non-zero coefficient that corresponds to the one which multiplies T1. So, this main diagonal we have got 1, rest are all zeros. For I is equal to 2, we have got A W that was equal to minus 1. The main diagonal, that is AP, which corresponds to AP, this becomes 2. AE was minus 1. Remaining terms are simply zeros. The same holds good for the third thing. minus 1 2 minus 1 0 0 0 0 0 and so on. So, we can continue in this way. So, what we will find is that we have got non-zero terms only on the main diagonals and remaining are all zeros, minus 1 2 minus 1. Now, let us write the last equation, 0 minus 1, and I will simply write this as AP n plus 1 because this is a bit more involved, we have written that earlier. So, if you look at this equation, look at the system matrix. System matrix is sparse, that is one characteristic. The other part is, what are the characteristics of the system which we have got? So, we have got this 1D heat conduction. This is the problem which we had been discussing. So, finite difference algebraic system. Two characteristics we can note. The first one is it is sparse, and the sparsity pattern is very clear. What is the sparsity pattern? It is a tri-diagonal system. So, the next module, when we discussed solution of algebraic equation, we will come across, or we will discuss one very important and very elegant algorithm which is called TDMA algorithm. So, that is, we can solve this system. So, it can be solved very efficiently using TDMA. This TDMA is an acronym for tri-diagonal matrix algorithm, and some people also call it as Thomas algorithm. Another observation which we can make is it is not symmetric. So, matrix A is not symmetric, though here the symmetry is really not of much importance, since a simple one dimensional heat conduction problem with a tri-diagonal structure, and this TDMA algorithm does not care whether a matrix is symmetric or not. So, this is just an observation that in this case we have got a matrix which is not symmetric by using our normal finite difference grid. So, next I am going to introduce you a small variant of what we have just discussed, and that variant is very important for flow problems. So, we will introduce what we call cell-centered finite difference grid. So, let me illustrate it using our 1D problem. So, in one dimensions what we had, we have a simple one dimensional domain, and for discretization we divided it into, let us say, n equal segments. The segments could be unequal, it did not really matter. Now, previously what we had done, these were the nodes, that is the points which mark our divisions, those were the ones which we have taken as our grid points. Now, let us make a slight departure. Instead of treating these dividing points as our computational nodes, Now let us take the points which are in the center of these so called divisions. So each of these divisions we can also call them, let us call them as a cell, and our computational node, which I would now put with a filled circle, these are our computational grid points. Okay. So what would be the difference compared to the previous arrangement? We will have exactly as many nodes, as many divisions we have made. So compared to previous discretization, this number of computational nodes is 1 less. This is now equal to n. Earlier we had 1 to n plus 1 nodes. Now as far as discretization of interior nodes is concerned, that would remain unchanged. So discretization of our governing equation at an interior node let us call this as interior node I, that would be once again the same. Remains similar to what we had derived earlier. But now there would be an important difference. How do we incorporate the boundary conditions? Now even the imposition of the known temperature boundary condition would require some ingenuity. We have to make certain modifications. So now let us come to the boundary nodes. That is, now let us have an incorporation of boundary conditions. So we will take two cases, one of our temperature specified. So case A, which we call Dirichlet BC, that is temperature specified. How do we tackle this case? So suppose now we are dealing with the temperature specified at node 1 as we have discussed in our specified problem. So now let us draw the cell, the first cell. So our computational node is sitting here at the center. The temperature is specified as boundary node. This is where we have got T is equal to T bar. Okay. What do we do now? We introduce a concept of ghost node or ghost cell. Ghost cell is something which does not exist in a physical domain, it is just an imaginary extension. So let us extend this toward the left hand side, and this dotted portion, this becomes our so called ghost cell. So we have now an imaginary computational node which we are going to use only for the sake of formulation. It will not come in our problem solution, and let us number it as 0. Okay. So we have got an imaginary node, or rather we call it as ghost node, 0. Now this would appear in our central difference approximation at node 1. So if we look at the approximation of our term d2 by dx square at node 1, this would be given by t2 plus t0 minus t1 divided by twice of t1 divided by delta x squared. Okay. So now this t0 is really not a part of our solution, we have just introduced it to handle the boundary condition. Okay. So in this case, while using self-centered thing, we would use our usual central difference approximation for all grid nodes 1 to n, 1 to so on up to n. Okay. And we will modify the equations corresponding to the nodes on the two sides which will incorporate boundary conditions at node 1 and node n. So now in this equation for the node 1, we need the value of t0. Now let us use a very simple averaging concept. So using simple averaging, T at 0, this can be expressed as an average of the temperature at T0 and T1. Okay. And now T0 was our specified boundary condition. Okay. So now you say that we can write this T0 as twice of T bar minus T1. So in the discrete equation for node 1, we need to substitute this value for T0, and that will lead to two modifications. This T0 is linked, what was the discrete equation for node 1? So discrete equation for node 1, this one was our AW T0 plus AP T1 plus AE T2 is equal to Q at point 1. So what changes we need to make? If we substitute for T0, that AW things would vanish, and the contribution we will have here is 2 T bar minus T1 multiplied by AW plus AP T1 plus AE T2 is equal to Q1, or rearrange it. So we can write it as AP minus AW times T1 plus AE times T2 is equal to Q1 minus 2 T bar AW. So now this becomes our modified discrete equation for node 1. For node 1. Now we need to adopt a similar concept for introduction of the boundary condition at the last node. Okay. And we have got a derivative in our boundary conditions. So what we would use, instead of using a backward difference approximation which is only first order accurate, which we had used previously. Now we would use a central difference approximation for the derivative at the boundary node. Once we would introduce this concept of a ghost cell or ghost node. In terms of the value at ghost node, we will write down our derivative, obtain the derivative, and then substitute the value of the temperature value at the ghost node in terms of what we obtain from our boundary conditions into the discrete equation for node n, which we had obtained by using central difference approximation for the interior node n. So we will again get a modified equation, okay, and that modified equation can now be coupled with the rest of the equations. Okay. Now these things we are going to discuss in the next lecture, and then we would compare the solutions or the system matrix which we get in both the cases, the one which we get from cell centered finite difference approximation or vertex centered grid, which we normally use in finite difference. And we will notice there is one very important difference, but for the time being let us keep our excitement contained for the next lecture. So next lecture, apart from it, we would also try and give one numerical example. We will solve a numerical problem and see which of these approaches, or vertex based approach, which is a normal finite difference approach, or this cell centered finite difference discretization, which one is more accurate. We will take one problem for which we know what the analytical solution is, so we can compare the two rather easily, and then we will move on to few more applications, and we will discuss the computer implementation aspects also in the next lecture.